Welcome to this webinar, as Martin already said. My name is Kevin, and today we're going to talk about best practices for building async APIs with the ASP.NET Core. Now, let me just get rid of this view. There we go. On screen, you can find a link to my GitHub. That's the location where you will be able to find the code of this webinar, so the fully completed code. I would say after the session, but it's already there, so you can already check it out. Now, we're going to talk about building async APIs with ASP.NET Core here, and I could actually make this a very, very short session, because if you're building an API and you want to async it, let's say, you simply have to follow a few rules. And one rule is start at the bottom layer. And the second rule is use async await all the way up to the outer facing layer. If you just follow those two simple principles, you're already going a long way towards creating a really good async API. That said, that would make this session pretty short. So I always think it's important to know why you do something instead of just knowing how to do something. So that is what we're going to start with today. We're going to start by looking into why we should write async code. There are advantages to it, obviously, but the main advantage isn't performance, as will become obvious quite soon. In fact, if you just write async code on your own machine, chances are pretty big you will see no performance improvements or even a slight decrease in performance. But the advantages will become obvious soon. Next to knowing why we should write async code, we're also going to look into how async works. So that means that the session starts with quite a bit of theory, but it is important to know and maybe to listen to again afterwards. But don't worry, there's quite a lot of code coming up as well. I think about 1/3 is the theory and 2/3 of it are code. So let's start with that theory then. As said, the main advantage of writing async code is not performance. The main advantage is scalability. But what does that mean then? It's a bit difficult to find a good definition for this term, as I find it being used across technologies with different ways of looking at it. So I tried to look for a good definition of it, and this is what I came up with. Well, in fact, Google came up with it, and I kind of liked it. So scalability is the capability of a system, a network, or a process to handle a growing amount of work. That's part one of the definition. So if your system, network, or process, or your API, the API you've written, can easily handle a growing amount of work, you are working towards better scalability. The next part of the definition is its potential to be enlarged to accommodate that growth, which means how easy can we enlarge the available resources, let's say, so it can more easily accommodate growth. And growth in this case are requests that come into our API. So let's have a look at that, because there are actually two types of scaling that can come into play. And async await only, and writing async code only really helps with one of these. First one, horizontal scaling. We're going immediately into an example. That green blob on the right, that's the server our API is running on. Can be a physical server, can be a virtual server. We send a GET request to get a set of books. No problem, our server can easily accommodate that. We send another one, still no problem. Third one, no problem. And then the fourth request comes in, still at the same time, more or less. So all 4 requests are being handled by our server at this moment. And now our server is starting to experience some issues. It's obviously not a very strong one. After 4 requests, it's starting to slow down a bit. And then the 5th request comes in, and now it's really slow, right up to the point where the consumer of the API might experience one of those service unavailable responses, which you definitely do not want to get. We can help this by scaling out horizontally. And what does that mean? Well, in essence, it means we are going to add additional virtual or physical servers to accommodate these additional requests. So we add one, and the fifth request can be handled, still a bit slow, but we're not getting a service unavailable error anymore. We add another virtual server, and there we go. Our 5 requests can be handled at the same time because we scaled out horizontally. Now, to allow for this, we of course have to write our code or our system or architect our system in a certain way. You don't just get this out of the box. So we should then write our API in a way that can easily accommodate this horizontal scaling. And one of the best ways to achieve that is through adhering to RESTful principles. So if you're building your application according to a RESTful architecture, you're already a long way towards enabling horizontal scaling. The reason behind that is mainly the statelessness of such a system. So if one request comes into server A, it doesn't matter that the second request or a third request comes into server B or server C, as the full state of such a request is contained in the request itself. Now, if you were to architect your application in such a way that some sort of session state is held at server level, well, that's already a bit harder to accommodate horizontal scaling, because then it does matter where the second request comes after the first request is done, if they are related, of course. So to accommodate for horizontal scaling, start with a RESTful system, or at least something that's stateless over HTTP, in other words. But that alone is not enough. The other components in your architecture can still hurt scalability. You can write a perfectly perfect HTTP web API or even a RESTful API. And if you have one database behind that, or you have a non-distributed cache in front of it, then that easily becomes the bottleneck in regards to scaling. So in regards to horizontal scaling, always look at the system as a whole, not just the code, but also the database, the cache, any other components that might exist in your architecture. Nice thing about this, or rather not so nice thing about this, writing our code async does nothing for this. It does not help with horizontal scaling at all, which means that there's a second way of scaling, and that is vertical scaling. We're back at the example we stopped at previously. So 5 simultaneous requests that come into our server, and it's really slowing down. And now we're going to try to solve this with a vertical scaling approach, which means we don't add additional servers, but we increase the resources at level of the same virtual server. And by that I mean you can add an additional, you can add a faster hard drive. You can add some more memory. You can increase the CPUs that are available on your server. That's vertical scaling at level of that same server. And this is where it becomes interesting, because this is what we can use async and await for, or async code for. So what we actually want to do is increase the vertical scalability at level of one server. So instead of having to add additional memory and having to add a better hard drive or add a CPU, we as developers can have an effect on this. We can write our code in such a way that that resource utilization is improved. That translates to better use of threads, or trying to free up a thread, which is the unit that handles your request. Try to free up that thread as fast as possible so it is available for other work. If more threads are available at a certain time, that means that we can accommodate more requests to our API. So that is what writing async code helps with, improving the vertical scalability at server level by improving resource utilization, thus by freeing up threads as soon as possible. So that's what we're going to do. That's why we write code like that. But to really understand this and to really understand why writing code in such a way helps and what it actually does, I think it might be interesting to look into how a synchronous request is handled by ASP.NET Core, and then how an async request is handled. So let's do that. We're looking at a synchronous request. We've got a thread pool there. So whenever a request comes in, a thread pool is provided from that thread pool to handle it. So this request comes in to our API and we require a thread. So far, so good. There are threads available on our thread pool, so we can get one. Then the code from our API, let's say our code hits our controller and that calls into a repository, which at a certain moment uses Entity Framework Core to call into the database. At this moment, we're doing an input-output call. So we're doing disk access, which means that there is no, the code isn't running anymore. Our thread is just sitting there, waiting for the call into the database to complete. It's doing nothing. And then a second request comes in, which also requires a thread. There's still a thread available on the thread pool, no problem. We eventually end up in our database, and the thread is just sitting there. We've now got two threads that are sitting there waiting, doing nothing, because they're waiting for calls into the database to come back. And then a third request comes in. And now we hit an issue. Well, we don't hit an issue. The issue is that we now have to wait for a thread to become available. At the moment, there isn't a thread available, so our request can't, or the code can't be executed. At that time, the first call into the database returns. Our thread handles the rest of the code after the call into the database, and the thread is returned to the thread pool. And now, and only now, that thread can be used to handle our third request. So this is what happens when we write our code in a synchronous way. Now, let's see what happens when we use an asynchronous request instead. So, call comes in, there we go, thread is required from the thread pool, and we call into our database. But instead of the thread just sitting there waiting now, it is returned, control is returned to the caller. And control might be returned right up to the thread being freed. So if there's no other input-output work or network traffic going on, and no other code has to be executed, we get that thread freed up to go back into the thread pool. The second request comes in, a thread is required again. We call into the database, that's an input-output call. That thread is no longer required at this moment, so it is returned to the thread pool. And this is quite nice. Our third request, if our third request would now come in, we would be able to easily handle that as we have threads available. But at this time, the first call into the database comes back, which means we need another thread from the thread pool to handle the additional work. This can be the same thread as the original one, but it can also be another thread. So just any thread will do in this case. And once that work is done, the thread is returned to the thread pool, and any additional requests can easily be accommodated by the available threads. So like that, we have ensured that we use the resources the threads does better than with synchronous requests. And the relation to performance here is then that not at the level of not at level of your own development machine, you're probably not going to see an increase in performance. You're going to see a bit of overhead because of all the context switching or threads that have to be fetched from the thread pool and used to handle the requests. But what can help performance is if you look at it at a bigger level. So if you think back about the picture we had in the beginning, if we increase the resource utilization at server level, we will be able to accommodate more requests at the same time, which means that overall the performance will, overall we will be able to accommodate more requests, which means the performance of each, which means more requests can be handled at the same time, which will increase the performance a bit, but not at the level of a single request. So that's how it's related. And that's it for the theory as far as async versus sync is concerned. So let's have a look at how we do this in code. And that's where it becomes interesting, because this is the code we're going to write. This is the keyword. These are the keywords we're going to use. You have probably heard from the async. You have probably heard about the async await keywords before, and you've probably seen them around. So let's have a look at what they actually do. When you mark a method with an async modifier, that does just two things, actually. It ensures that the await keyword can be used inside that method. That's one. So if you don't mark it with an async modifier, you cannot await any code inside of that method. And the second thing that it does is it transforms the method into a state machine. Now, we will come back to this and why this is important. But for now, just know that that state machine is something that's generated by the compiler behind the scenes, which is what happens when you mark a method with the async modifier. It's a slightly little bit of overhead when you compare it to a non-async method, by the way. But well, the benefits are worth the overhead. So that does mean that marking a method with the async modifier does nothing in regards to having async calls. That's what we have to use the await operator for in combination with the async modifier. So what the await operator actually does is once you await an async method, it tells the compiler that that async method cannot continue until the awaited process is complete. So that's the moment when when control is returned to the caller and can be returned right up to the thread being freed. That's when this happens. Because if the compiler knows that the async method cannot continue until the process is complete, well, it also knows that it doesn't need the thread anymore in this specific method, potentially the calling methods. Okay, so it returns control to the caller of the async method, which I just explained. So that's these two methods. Now there are two things of importance with these keywords, and that is that a method that's not marked with the async modifier cannot be awaited, and that has to do with the state machine, by the way. We'll get back on that. And if an async method doesn't contain an await operator, it simply executes as a synchronous method does. So this is important. Just using the async modifier does not mean that your method will contain async code. Now let's have a look at a code example to clarify this a bit. So we've got a few methods here. Say the first method you see there, my action that calls get books async. Imagine that that's a method on your controller, an action on your controller. It returns a task of action result. The second method you see there, well, imagine the get books async method. Imagine that that's a method in your repository. And then we have another method, calculate book IDs for user, which is just a synchronous method, which I'm going to use to show you what happens. So our my action that calls get books async method awaits the get books async method. So the get books async method gets called, and we reach the calculate book IDs for user. This is just a synchronous call, so we nicely run through right until a few IDs are returned. Control is back in our get books async method, and now we are awaiting a statement into eventually our database. This is Entity Framework Core at work. So we're calling into our database and we're using a toList async method, which is also an async method, which is why it can be awaited. And this is where it becomes interesting, because by calling await here, control is returned to the caller. And if that caller also just has an await method here, as you can see, it is waiting for the getBooks async method to be complete. Well, that getBooks async method obviously isn't complete yet. What will happen is that control will be returned to the caller of this action on our controller, which eventually leads to the thread being freed up. So at this moment, we have an additional thread available. At a certain time, however, we require a new thread, which is after the call into our database is done. That thread handles the rest of the method, and the books are returned. So that's how the flow is when you use an async and await keywords throughout your code. Now, this is the last part of a theory before we dive into code. We noticed, let me go back. You may have noticed that the return types here aren't just an IEnumerable of book. The return type of getBooks async is a task of IEnumerable of book. There must be a reason for that, right? Oh, this is why that's the case. There are a few possible return types for async methods. The most important ones for us are task and task of t. Task of t means that the result of the operation is something of type t. In our case, a book or an IEnumerable of book. A task doesn't have a specific result type. So what such a task represents is a single operation that usually executes asynchronously. And those operations are important because we somehow need to be able to manage these operations. So we need something that represents such an async operation. That's what those tasks and task of t are for. So through that, we have a representation of the execution of the async method. And that's important because, as we just noticed, we need to be able to know the state or the status of such a method. We need to be able to know that, or our compiler needs to know that somehow, because we need to know when control can be given to the caller and when we need control back, so when we require another thread. So this is again part of the bigger picture. And through those operations, task and task of t, we can ask the status of such an operation. So whether or not it's completed or still running. When the method completes, it gets the status complete, and it returns the method's value as the task result if we're working with a task of t. And this is where that generated state machine is coming back. Because we're almost at the end of our story. We know how to use the async await keywords. We know how they allow giving control back to the caller. We know what represents such an async call. It's a task and a task of t, such an async operation. But we still need some kind of component that regularly checks these operations to see whether or not they have completed, and if they have completed, return control to the method. And that's what that state machine is for. So this is what happens behind the scenes. The tasks are managed by the state machine that's generated when a method is marked with the async modifier. And that completes the story. If you combine these components, then you know how async code actually works. So that's quite a lot of theory. And before we dive into code, and I promise it's mostly code from now on, there's just one more thing. You might have noticed, if you've worked with async await before, that void can also be an async return type. It can be, but it's really only advised for event handlers. There are a few reasons for that, but let's just say that this is something you would use if you're building a client-side application, not something that executes on a server. So if you're building a Xamarin app, or you're building a UWP app or something like that, you will often use void as a return type for an async method, an async event handler. This is not advised on server level because, well, we don't have an easy way to notify the calling code of our status, which makes it quite difficult to easily return control to the correct caller. And then there's one more, and that's a new one in C#7. I'm just going to put it on screen here. You can probably read it if you want. There's a new type that was created in C#7, if I'm not mistaken. That can also be a valid async return type. The reasoning behind this is that task and task T are reference types. reference types do have an effect on memory allocation. By allowing this new getAwaiter method in C#7, we can now actually have value types return type, which is faster and is better for memory allocation. It's probably not something you're going to write yourself. It's something that the people who created .NET Core tend to use often, because it is one of the reasons that ASP.NET Core is so much better at, so much more performant, or can be so much more performant than older versions. Okay, and with that, it's finally demo time. So let's have a look. All right. I have a starter project here, which contains a starter solution which contains 3 projects. The main one we're going to be working with is books.api. I'm going to ignore bookcovers.api and books.legacy for now. We'll get to that later on. What this is a pretty run-of-the-mill API. It exposes a set of books through a controller. This controller, by the way, contains no real code yet. It contains a simple constructor in which I inject a few things we will use later on. All the rest here is commented out, so it in fact does nothing. By the way, I know what you're thinking now. All those regions, I don't like regions. Well, don't worry, I don't like regions either. The completed code on my GitHub contains almost no regions, unless when I want to add something as an example. The reason I tend to use regions for this and comment out code is that if I were to type everything that I'm trying to cover today, I would probably need double the time. So it's not that nice to look at seeing me typing for 20 minutes in a row. So that's why I tend to use regions and comment out code. But we will look into it in detail. So we have a controller which talks to a repository. So you can see that the iBooks repository is injected here. And if you have a look at that, it's at the moment, it's an empty repository. And you can already see that we're going to cover quite a lot of use cases here thanks to the region naming. The repository in turn works on an entity framework core books context, which exposes one DB set, a set of books. The entity framework core obviously works on an entity model, so we have an author and a book here. That's the entity model that represents one row in a table in this case, because it's a pretty straightforward example. And then we also have a models folder which contains the DTOs, the outer facing model. And AutoMapper is used to map between these. So all in all, this is probably how most people will build a standard API to get started with, I think. So the first thing we're going to do is start at the bottom layer. As I said, always start at the bottom layer, which in our case is our repository, because the real bottom layer, that's our data access layer. For that, we use Entity Framework Core, and that already has support for async. So let's start typing a bit, why not, instead of just commenting it out. We're going to write the first method in our contract. And the first thing that pops up here, as well, let's try one, to get one book, get book with ID, why not, something along these lines. The first thing we notice, always return a task of a type in this case. So the return type is a task of book. But what we have to talk about now immediately is the naming of this. So should we use getBook or should we use something else? Like you can see if you look below here, getBook async. Well, it's not a rule set in stone, but the Microsoft guidelines on this advise that for public methods, which depends on the implementation, of course, because this is just a contract. For public methods, we should use that return tasks and are expected to execute async code, we should use the async suffix. There's a reason behind this. Well, there's two reasons behind this, actually. One reason is that this makes it easier for the consumer of our repository, for the developer that has to consume the repository, to know whether or not a method is likely to contain async code. That's reason one. Second reason then is that this allows us to combine synchronous and asynchronous methods in the same class, which is a use case you see used often in built-in .NET or .NET Core classes, where you have async methods and synchronous methods that essentially do the same. So we are going to use getBook async. One thing you also notice here is that the getBook async method doesn't contain any modifiers. There's no async modifier here. The reason behind this is that the async modifier is an implementation detail, whether or not we're going to want the compiler to generate a state machine from this, and whether or not we want to allow using the await keyword inside of the implementation. Well, that's a decision that has to be made when we implement it. So as an interface isn't an implementation, it's a contract. The async method doesn't belong here. And in fact, it won't even compile if you write code like this. You can immediately see, well, that's a bit of a weird error. You can immediately see, that's the one. No, you can immediately see an error, it won't compile. So let's get rid of that. Or maybe like this. Let's just get rid of that. You will have to believe me when I say that it won't compile. All right, now let's implement this. We see here that the writer is telling me that the books repository contains some sort of mistake. So let's have a look at what that mistake might be. The repository contains just one constructor. Again, I just inject the book's context and a logger, which we will use later on. But that's it. For the rest, none of these methods have been implemented. So let's implement getBook async. Something along these lines. And we want it to return a task of book. That should get rid of our error. What we want to do in here is, well, first, of course, we want to check the input. So we check whether or not the GUID is empty. So if ID, am I the only one who tends to say to himself what he's writing? I always notice that, even if I'm completely on my own, sitting there at my desk, I'm constantly talking to my laptop. I'm not sure if that's still healthy, but well. So we want to throw an argument null exception when the GUID is empty. Now we pass through name of ID. So far, so good. And then we want to return something. And what we want to return is, well, one book. So let's give that a try and see what we have here. On the context, we have books. And on that, I can, well, let's say I want to include the author as well. And I want to get the first one that matches the ID. Now you can immediately see that we have quite a few options here. We have first or default, but we also have first or default async. This is important. That, by the way, is one of those methods that return that, by the way, is one of the methods that's from Entity Framework Core. So if you want access to those, you need to add a using statement to Microsoft Entity Framework Core. By doing that, you get these methods. So let's say first or default async, where the book ID equals our ID. That should take care of this.
Now, this works and this will compile. So far, so good, right? Well, not exactly. The problem is that we are not awaiting anything inside of this method. That means that the task will just be returned to the caller. That also means that we are actually leaking a task that should be contained in our repository, or leaking implementation details of our repository outside of our repository. So this is a pattern I sometimes see people use. Don't use async await in methods that are async, but just let the task bubble up and handle it in the caller code. That obviously is a leakage of your repository, so that's not something I would advise to do. As we know, to make this method async, we have to use the async modifier. So if we do that, we run into another problem. With that async modifier, we don't want to return a task anymore. We want to return the result of the actual task. So we want to await this statement here. So this is an actual async awaited call into our database now. And like that, we already have our first method asynchronously. Now this is an easy one, right? We're just getting started, of course. Now, the next thing is using this method from a controller. So we want to call into this method from our controller. So let's have a look at our books controller. And let's say we're going to write, well, one action to get one book. So the template is the ID. And let's say it's a simple method as you would typically write it were you not to use async code here. Get book and do it ID. Something along these lines. And then we want to call into our repository. So we need the entity. Oh, let's say books repository, and on this we should have get book async. There we go. And like that, we expect to get back the book entity. That, of course, is not going to work because it returns a task of book. That's a bit of an issue here. We don't want a task of book here because that would leak it outside of the repository again. We want the actual book. Now, how do we do that? Well, there's one way of doing that, and that is by calling result on our task. By calling result or wait on the task, we will end up with the actual result of the async operation, which means result returns. Result, as you can see, gets the value of this task, which means that is an actual book entity. So now we can continue. Oh, let's do a quick check. Need to ensure that the book entity is null, because if it is, well, this method should return a not found. There we go. And then we return it after mapping it. So this is AutoMapper at work. We map to a book model, and what we map is the book entity. All right. Well, I think we should give this a try. Let's see what gives. There we go. And it should launch any minute now. All right. So let's try getting a book. And this works as expected. But the question is this a good idea? I don't know if I mentioned it, but I'm going to write quite a bit of bad code before we end up with good code. And this is actually an example of bad code. And why is that? Well, if you call .result on a task, you're actually blocking the thread. And by blocking the thread, well, we are not improving scalability. On the contrary, this is exactly what we do not want to do, even though it will definitely work. Now, how do you do this then? Well, we use the async wait keywords. So we make this method async, and we want it to return a task of action result in this case, and we no longer call .result on it. Instead, we await the call into our repository. All right. This is also why I'm not gonna keep on typing. I tend to make a lot of typos, as you can see. Let's give this another try. There we go. And let's call into this. And here's our book again. But this time we have correctly written our async code. It's quite easy to make mistakes like this, by the way. Because well, tasks are also used for parallel programming, and well, they allow things that shouldn't be used for async await and other things that shouldn't be used for parallel programming. So it's sometimes a bit difficult to know what's going on. But this goes back to the original rule I talked about in the beginning of the webinar. Always use async wait all the way through your layers. Don't use something like .result or .wait if you can avoid it. All right, so we've written a bit of code now, not that much yet, but we don't really know what we should write async code for yet. I've just been writing some code. So let's have a look at what types of work can we use async for. Well, there's two types of work that can happen. One is IO bound and one is computational bound. And IO bound work is something that you can define by asking yourself the question, will my code be waiting for a task to be complete before continuing? We've already encountered this. We've seen that. It's file system access, database access, network calls, stuff like that is input-output bound. This is a very good candidate for using async code for, both at side of the server and at side of the client. And then we have computational bound work, and that's a bit different. The question we have to ask ourselves then is, will my code be performing an expensive computation? If that is the case, you can probably be dealing with some legacy code or an expensive business algorithm, something that takes a while to calculate. This should only be offloaded to the background to another thread or use async await for when used on the client, never on the server. And I'll get to the reasoning behind this soon. But this is important to already remember. Do not use async on the server for computational bound work, even though it's something that I would tend to do. It feels like something to offload to another thread or something to try and offload to another thread. It's not actually possible. It's something that would urge me to write async code for, yet it is a bad idea. And we'll get into an example quite soon. First time for another demo surrounding this. And you'll immediately see the reasoning, the difference between something that's IO bound and something that isn't IO bound. So something that warrants async code and something that doesn't. Because our next action we want to add on our repository is a call to add a book. Now let's start with add book async. So we're adding a method add book async, which returns a task. So when you add something via a repository, you tend not to return the entity, which means we use task without a return type. And the entity you want to add is the book to add. So far, so good. Let's go to our repository. And we have an addbook async method here. Let's uncomment that, which is much like the getbook async method we've just written. So I check if there's actually a book to add that's injected or inputted in our method, and we call add async on the context. This looks pretty logical to me to write code like this, right? There is an add async method on the context. We can use async await for this. This will compile, this will work. But now we have to ask ourselves the question, is this a good idea? What happens when we use Entity Framework Core and we add a book to our context, or we add an entity to our context? That's the question we have to ask ourselves. Well, what in fact happens is that the entity is starting to get change tracked at that moment. So from this moment on, the context can track the stats of the entity. What doesn't happen is an I/O call. When we just add a book to our context, there is no communication with our database yet. Communication only happens once we save the changes on our context, once we actually persist the changes. So in our case, this is not a good candidate for using async. And if it isn't a good candidate, you shouldn't use it, because even though it's small, there still is a bit of overhead for writing async code. If only for the state compiler that has to be created and has to follow the status of your operations. So don't use async code when you don't need it. That brings us to the next question, obviously. Why does that add async method even exist? Well, the reason behind that is that sometimes for some use cases, you might need a call into your database when something is added on the context. And that's, if I'm not mistaken, through a SQL value provider. A good example might be something that automatically generates IDs at that moment before persisting it, or something that requires a value that's dependent on other values in your database which aren't on the context. But this is quite exceptional. If you need that, you will know it from the way your database is structured and from the requirements of the app you're building. So for most cases, add async is a really bad idea. So we're not going to use that. Let's get rid of this. Instead, we're going to use add book. That makes much more sense. We're not doing any IO bound work here. So to implement that, well, that's the add book region here. There is probably nothing out of the ordinary here. It's a simple method to add a book on a context. That's it. And that takes care of adding a book. No IO bound work. But obviously at a certain time we have to persist our changes. And that's when IO bound work does happen. And that's how we get to save changes async. This is a method that does IO bound work. So we want it to return a task, and we mark it with the async modifier. The async suffix. And in our repository, we then implement this. And we return whether or not items have actually been persisted. So again, an async modifier, bool as the return type, bool as a result of the task, that's the return type, and we await the actual call into the database using the async version of save changes on our context. All right. Now let's use this from our books controller. Let me just get rid of this code I typed here. I have slightly more complete code standing here ready. So that's our getBook method. The only difference is that we're now naming the route. And we have a createBook method here, which will call into our database. So the same principles apply here. We make sure it's marked with the async modifier. We have it return a task. We don't await the call into addBook, but we do await the call into save changes async. Lastly, we refetch the book from the data store, so we have the additional author. And that's it for this method. Let's give that a try. All right, I think it's up and running. Great. I think I have a sample request ready here. So we send a post request to API/books. We make sure that the content type header is set to application JSON. And in the body, we add an author ID, title, and description. So a JSON description of a book for creation in this case. Let's send it. And there we go. We get back 201 created. So we should be able to find our newly created book here through the location header. Let's have a look. Let's give that a try. And that indeed works as expected. So we now know how to use async code for getting, reading data and for inputting data. But what is next? Well, there's something like legacy code. Let's go back. Often you end up in a situation where you have to integrate your API with code that's been around for quite some time. It might have been created by another team. You may not have access to the source code. You may not be able to make that code async aware. It's just legacy code. And I've got an example of this here. A very complicated page calculator. This just simulates a full CPU load for about 5 seconds. It's called calculate book pages. And somehow each book in my collection has exactly 42 pages, apparently. It takes 5 seconds to calculate that. This is code we want to execute from some other part of our API code. So let's say we want to execute that in our controller to give this a try. All right. Now, we can do a few things here. We can call into that code directly, or we can try and make it async. Let's try making it async first, because it's pretty cool code. So let me show you. What we want to do, or what we need to do, let me just comment this out again, and we're on the next one. What we need to do is try and make this calculate book pages method awaitable. So if I copy paste that here, I cannot await this. It just returns a set. It just returns 42. So there's no way to call await on this. But what I can do is create a task. Create a task which can be awaited. So we're now creating a get book pages operation actually, which can be awaited because it's async and it has a return type of task by which int contains 42, the amount of book pages. And in this method, we call task.run. With task.run, we can actually start a new task for synchronous code. So we are now making our synchronous code behave in an async manner by using task.run. From this moment on, that means we can actually nicely await it. And let me put a breakpoint here to see if this actually works. So let me give that a try. All right. Let's try and get a book. This will take at least 5 seconds. Oh, or not. Has it started yet? Oh no, I'm a bit too fast apparently. Is this still waiting? Let me just start that again. Let's give this another try. Or what was, did I get output? No, I didn't get any output. Let me see here. Oh, this should be okay. Let me give that another try. Up. There we go. Build succeeded. And it's trying to start up. It's initializing the debugger. There we go. I was a bit too fast. There we go. All right. So now let's try getting a book. Should thus take at least 5 seconds, which it obviously does. Takes a bit more even. I hit my debug statement. And let's have a look. We get back 42. So far, so good. So this actually works. Now, let's see if I can find the actual threads that have been used. If we look at the debug output window, we see that the thread when entering getBook was thread number 8, and when calculating the amount of pages was thread number 7. So this means that we have actually offloaded something to another thread. And, well, that sounds pretty good, right? Well, not exactly. And let's learn why. So, should we offload code like this, legacy code, to the background using task.run? And remember that this is a pretty heavy algorithm. It's 5 seconds of full CPU load. Well, to answer that question, we're going to look at what actually happens when we do that, when we use task.run on the server. So this is a bit of pseudocode. We have a getBook action, and in that getBook action, task.run is executed, which in turn calls into getBook pages. That's the code we just saw. So let's start at the beginning again. Our getBook action is being executed, so we obviously need a thread for that. Then task.run gets called, which requires another thread. That previous thread can now be returned to the thread pool because we no longer need it. We are awaiting this call. And at a certain moment, task.run is done, so that thread is returned to the thread pool again, and a new thread is required to continue with our getBook method. So this is essentially the flow of what happens when we use task.run on the server. If you don't use task.run on the server, well, there is no thread switching like this. That yellow circle there for getBook, well, that gets used for getBook pages as well. So should we then use task.run on the server? Well, we shouldn't, because ASP.NET Core is not optimized for this. It was never intended to allow task.run on the server, even though we can. The reason is that it does creates an unoptimized thread. So that second thread we had there, that's not optimized. And next to that, it also causes overhead. In essence, it means that this actually decreases scalability instead of increasing it. So this is definitely not something we want to do. When task.run can be used, where task.run can be used is on the client. So in a Xamarin app, it can be a very good idea, because in a Xamarin app, you can offload CPU-bound code to the background using task.run. Great example is keeping your UI responsive. If you either use async await all the way through, or you use task.run to offload something to the background to make sure your UI thread isn't locked. So task.run on the server, very bad idea, never do it. Use it on the client. That does mean I still have to correct my code a bit here, but that will be a very quick and easy fix. So instead of calling into our get book pages method here, we simply execute our code synchronously. So this is another example of when it's not a good idea on the server to write async code. Instead, just execute it synchronously as it was intended. That's probably the best you can do. All right. I have a few more things I want to tell, so I hope you don't mind me going over time a bit. Let's have a look. I still have a few demos as well, by the way. So one of the questions that often gets asked, especially by people who've been using async await in the full.NET framework, is, well, what about synchronizing? So this is a bit of more advanced stuff. What about synchronization context? Well, there's very good news. ASP.NET Core doesn't even have one anymore. The old ASP.NET does. In ASP.NET Core, it's a thread pool context that's used for synchronization. So it's no longer the responsibility of us. It's the responsibility of what goes on behind the scenes. We do not have to keep this in mind anymore. And that's great because this improves performance. There's a lot less context switching in code. And next to that, it's also easier to write async code like that without having to keep that synchronization context in mind all the time. So this is a pretty good idea. And something that's also important, if you've written async code in the full.NET framework before, you know that you can easily end up with a deadlock by calling task.result in some cases. Well, that doesn't happen anymore in ASP.NET Core. The deadlock is gone because of the missing synchronization context. But you still shouldn't use it because it blocks the thread. So don't do that. And then we have one more. What about configure await? That's another one of those questions that often gets asked. Well, configure await is initially intended to configure the task so that continuation after the await doesn't have to be run in the caller context. And here's that context again. Well, initially this would avoid deadlocks, or at least it used to, but we don't have a context anymore. So we don't need configure await false anymore when we write async code in .NET Core. This again makes our life easier. But, and this is quite important, configure await false is something you might use in a class library, something you want to make available for other people on your team or other people in the company you work for, or maybe as an open source project. The thing is that you can run ASP.NET Core code or code like we write, both on the full.NET framework and on ASP.NET and on the .NET Core framework. In fact, the main thing I would do these days when writing a library is make sure it targets .NET Standard 2.0. But something that targets .NET Standard 2.0 can be consumed from full.NET and from .NET Core, which means that in one case you do have a synchronization context and in the other case you don't. So I would still advise to use configure await if you think that your library might be used by people or by code that targets the full .NET framework instead of .NET Core. If it's full .NET Core or if it's only .NET Core, there's no reason to use configure await false anymore. All right, I have one additional demo, and this is one that covers a bit of a different use case. So a lot of APIs often have to communicate with other APIs. And this allows me to explain cancellation and waiting for tasks to complete. Something you will definitely come into contact with, even if you're using HTTP client on the server. Then you will also come into on the client. Then you will also come into contact with this. So what often happens is that an API integrates with another API. We have to call into another API, and that is definitely an I/O call. It's a network call, which we use HTTP client for. That's why I have that book covers API here. So this is a dummy API. Let's have a look at what it does. It allows returning a random set of bytes which fakes book covers for a book. So it's one method which accepts a name, which I simply do to make it to enable diversifying between fake book covers, and it also potentially accepts a return fault parameter, which allows me to simulate a 500 internal server error to explain cancellation. So in fact, a simple method that generates a fake book cover which can return a fault at wish. We're gonna call this one. And let's open our repository contract again. I add one method, getBookCovers async, which returns a task of IEnumerable of book cover. So far, so good for a specific book. What I want to explain now is how we can not just call into another API, because for that you just use HTTP client, but how we can call into that other API multiple times at the same time or right after each other, because it's different. So first of all, I'm going to uncomment my second constructor, which we're going to need because I am using HTTP client now. So that means I need an HTTP client factory to create an instance of it. Let's get rid of this old constructor here. There we go. The cancellation token source is coming up next. So the only thing that's different from this constructor is that we now inject an HTTP client factory. Now let's have a look at the method to get a set of book covers. I'm immediately gonna run through it because it's quite a bit. This is why I don't type this, by the way. It would take way too long. So the first thing I want to do is create a new HTTP client so I can integrate with my other API. And then I want to create a list of URIs I want to call. So say this book has 5 potential covers, one for Europe, one for the US, one for India, one for I don't know which country. So this is quite a common scenario. And we can now start calling this. And you can already read it here actually. We can just run through this with a for each and await each call into HTTP client.send async, something along those lines. So we just execute HTTP client.send async one after the other and we await each call. And that's good, that actually works. But there's another approach which allows us to start executing code faster, and that is executing this in parallel. So instead of using async await, we are now going to using async await and for each. We're now going to create one task to download one book cover, and in this task, in this method, we call into get async on HTTP client for a specific URI. Now, this means we now have a method that can be awaited and that can be executed in parallel. We do that by creating a list of tasks for which we simply create a list of tasks from each download book cover async method. So that's that return type here. And we then start these tasks by enumerating over them. So from the moment on you do that, the tasks are started. Now we want to wait for all these tasks to complete. So we return await when all on task for this download book covers task. Now, why do we do this like this, and what is actually going on? Well, what this will do is run these tasks in parallel. So we will have parallel execution of our 5 requests here, which also means that whenever one request comes in, we already end up in the response.isSuccess status code part of our code, or at least after the get async call here. That means that we can start executing code on the book cover that comes in as soon as it's done, instead of having to wait for each one in the row before we can execute code on it. And that's a small advantage. Let's have a look at what happens when we actually do that. So for that, I need to call into get book covers async somewhere. So let's do that as an example from our controller. There we go. So this is just small sample. Get book covers async is called here. And then we will look at the output window to see what actually happens, because as you can see, I am logging. There we go. I am logging when the download completes for a certain book cover. Let's give that a try. And let's get one book. Oh, I see an issue. The issue here is that I just started the books.api project. So that's not good. I need to start my book covers.api project as well. And in Rider, that means creating a compound project. If you ever need to do that, you can actually via the, where was it? Well, somewhere here, I'm not sure where exactly the edit configuration part is again. But anyway, if you find the edit configuration window, it's there that you can create a compound project to start both APIs. All right, let's try that again. There we go. This does take a bit longer, which makes sense because we're now generating fake book covers. And there we go. By the way, I do not return the actual bytes here because that would take way too long. And we see we get back our book covers nicely in order. That's quite odd because I have been telling you they would run in parallel. Let's see what actually happened. Let's have a look at the output window. Console output. Let's see if I can actually find it. What am I actually calling here? I am looking for my calls into. All right. Seems like I should run in debug to see this in the output window. All right, I'm going to do this slightly differently. Sorry for this. Let me set a breakpoint here. Let's just do it like that. The build succeeded, so far so good. There we go. And let's try getting a book cover again. Let's wait until we hit the breakpoint. Did I mention I need a new, faster laptop? I don't think I mentioned that yet.
It could be that writer already hits the breakpoint.
Ah, thank you for that. All right. So let's continue. There's a little problem with my environment, I think. Here we go. This is the first one that comes in. And if you look at the actual URL that's being returned to URI, you see that it ends in dummy cover 5. So this was actually the 5th task, which does prove that these come in when they're finished and not in the order they were executed. All right. Last part is cancellation. It'll only take a few minutes, I promise. But it is important. As you probably know, you can cancel tasks as well. So let's have a look at what happens then. Most items, let's uncomment our cancellation token source here. So most calls or most parts of ASP.NET Core that work with tasks can also allow those tasks to be canceled. And this is important because if a task is not canceled when it's no longer needed, then it keeps on using that thread. So cancellation of a task when it's no longer needed ensures that the thread is freed up again, which again increases or helps with the scalability of our application. So it's always a good idea to cancel tasks when it's possible. Now, the thing is, you don't just cancel a task manually, or at least not if you're using HTTP client. You ask HTTP client to cancel that task for you. And for that, you need a cancellation token and a cancellation token source. So that's what I did here. I used the cancellation token source and new it up here. And I pass the token on that cancellation token source through to my download book covers async method. Now, when we call cancel on the cancellation token source, so when we actually cancel, what happens is that every component of your application that accepted that token will get notified of this cancellation. So what we actually do when we call cancel is say, well, could everyone who accepted this token now please cancel itself? That's the only thing we're doing. So I call into download book cover async. Let's have a look at that. And we pass through the cancellation token to the get async call. It's this that allows HTTP client to cancel its tasks. And when do we want to cancel a task? Well, remember that the book covers controller allows us to fake an internal server error. Well, when an internal server error happens for one of the calls, to get the book covers, let's just say we want to cancel all the other calls. All right. Let's have a look again how we do that. So if we have a successful response status code, we just continue as usual. If not, this is what will happen when we get an internal server error. We call cancel on the cancellation token source. And that in turn will ask HTTP client to cancel all remaining tasks that may or may not be executing. So to catch that error then, that's the last thing we have to do. We surround our task.when all statement from the previous demo with a try catch, and we catch an operation cancelled exception. That's the exception that gets thrown by HTTP client when the actual operation will be cancelled. So this is what we actually want to catch, and then we can log information to the output window if needed. All right, let's give this a try. And I don't think I need a debugger for this. So let's try this. Should be pretty fast. Yep. And there we go. Let's try fetching a book. And this time you saw that the request returned much faster. And that's because, well, book covers is empty here. That's because all generation and transfer of those fake bytes of book covers were cancelled because we actually called cancel when this URI was executed and returned with an internal server error. So this is what happens then. And if we look at the output window here, we can actually see the tasks that were cancelled. So you can see task 1 cancelled, task 2 ran to completion. That's our return fault call. And all the other ones were cancelled as well. This means that we've freed up 4 threads that would otherwise be in use still. So that is really a big advantage of cancellation. You should always do that if you want to increase the scalability of your application. And with that, I did run a bit over time. I'm very sorry for that. But I do hope you found the session worth your time. You can find the demo code on the link you see on screen. And that's it for my part. Martin, if there are any questions, I'd be happy to answer.
We actually have a couple of questions. So first of all, thank you for presenting. I think it was very interesting, and I don't think anyone actually bothered that you went over time a little bit, so all good there.
Okay.
Also, apparently there are a few people who tell themselves what code they are writing, so you're not alone there.
Okay. I feel a little less weird now. Great.
Yeah. So a couple of questions that popped up. One was, is it a good idea to use async await with entity framework and a database?
Yes. That's that is one of the great reasons to use it, because once you call into a database, you're doing an I/O call. So that's something you definitely want to use async for.
Okay, cool, thank you. Now, in the last example you had where you were parallelizing things, what happens if one of the external HTTP calls fails or throws an exception while being executed in that parallel?
Well, that's why at the end I used a try catch. So if something like that fails, that has the exact same result as the fake fail we did at the end. So in the last example, I faked an internal server error. Any faulty response type would do. I used an internal server error. What happens is that the other tasks keep on executing until you actually cancel them. So cancellation is here very important to implement because you want to ensure that for the scenario of the person who asked this, you want to ensure that if something goes wrong, so if the server isn't reachable or something like that, you will also get an operation cancelled exception. And you want to ensure that once that happens, all the other tasks are cancelled. And the only way to do that is by calling cancel on the cancellation token source from which you pass through the token to your HTTP client call. So unless you cancel them, the threads will keep on being used until all the other calls will also reach a faulted or successful state.
Okay, that makes sense. One other question just came in. What if you have an awaited call on a database and you know that usually that database call returns in under like a millisecond, for example? Do you still async await there or not?
I would still async await there because you don't know what might happen with that database in the future. It wouldn't be the first time I was working on a project where a database call would work perfectly, and then some other component of the application would insert a lot of data, which would screw with my indexes a bit. After which that call would take a lot longer. So just to be sure for any future changes that might happen to the database that might make it go slower, I would, as a rule, still use async await here, yes. Even though for the call that is currently 1 millisecond, it's probably not going to help a lot. It might even make it slightly worse. And may I add something to this? It's always a good idea to test code like this. I haven't been able to show it in the webinar. I already went over time a bit, and I think normally this is something based on a course I made, which is about 3 hours. But a good tip I can give you: look into web search. That's a tool that's WEBSURGE. That's a tool that's used for load testing. And with that, you can easily test whether or not the code you've written or asynced was actually gave you an advantage or not. So if you're not sure about something, the best advice I can give you is test it with a tool that allows load testing, like web search.
All right, thanks for that. And then maybe one more to close this off, a coding question. So it was actually during one of the first demos that you showed where in the controller's constructor, you would take in a lot of parameters and check them all for null values. Now, since everything uses DI in the background, someone was curious about why you would still add the null checks in there if the container always provides the dependencies.
That's a pretty good question. Well, my reasoning behind that is that the container itself can be, you don't need to use ASP.NET Core's built-in dependency injection container. By default, it uses the built-in version, but you can easily implement or inject your own IOC framework there, which might be an open source framework, which might be something of some kind of framework you have to use inside of your company. And I know I can trust the built-in container in ASP.NET Core, but I can never be sure what container will actually be used. So just because you can override that container and someone else or some other team or some other code you have to use can potentially use another IOC container that may or may not have bugs, I just make it a habit to always check my input parameters, because I simply don't know which DI system will be used in this case.
All right, thanks. Since we are out of time, let's quickly switch to my screen so I can give everyone the resources on where they can find the recording afterwards and so on. So let's do that. First of all, again, thank you for presenting this, Kevin.
You're welcome.
If you have any more questions or want more information about Rider or try it out, you can find our website, you can ask us on Twitter, and we'll also announce the recording both on Twitter as well as on our blog, probably somewhere near the end of this week. With that, thank you everyone for joining, and thank you, Kevin, again for presenting, and we'll see you all next time. Thanks.